Okay, in this video we will discuss about how entropy changes when a substance changes state. And particularly that's going to be pretty useful when you are looking at a chemical reaction. I mean, you can write a change of state in terms of a chemical reaction, but if it wasn't a change of state, you can still predict how the change in entropy is for a particular process just by looking at the state in which those substances appear. So the main concept here is just to remember that entropy increases as you move on or from one state to the other. If we start with a solid state, then the solid state will have a lower entropy than what a liquid will have, and the liquid will have a lower entropy than the gas will have. And basically, remember that entropy has to do with in how many different ways you can dissipate energy in a particular system. In the previous video, we were discussing that in terms of how many microstates and how many different ways you can represent a particular system, right? When you are looking at a same substance, but like different state, then the same concept when in terms of disorganization applies to this concept. Remember, if you have a solid, what is the characteristic of a solid? If we go really back to 170, then we have that a solid, number one, has a fixed volume, and number two, has a fixed shape. And let's focus on the part of the shape, okay? Why are the solids on a fixed shape? Well, that's because those particles are really close to each other, really close in the sense that they are touching each other. The relative position of each particle is fixed with each other, okay? So they are in a tight packing, if you will, in which the particles are interacting with each other. They are not moving relative to each other, so they are in a fixed position. Basically, they are not allowed to move, just to vibrate. So if we are looking at ways to dissipate energy, well, the solid doesn't have that much ability to do so just because the particles are really close to each other. Okay? So solid. The particles are fixed. Fixed in position. Okay? So they cannot move, so they have limitations in terms of in how many different ways they can dissipate energy. That restriction is not completely eliminated, but the liquid particles, they are still very close to each other, close in the sense that they can still interact with each other, but because they can move past each other, then they are adding dimensions in which they can dissipate energy. Okay? So in a liquid, there are still interaction between particles, but because they can freely move, then there are more ways in which they can dissipate the energy. And when you have the gas, well, they have. Let's put it this way. In a gas state, the molecules are so far apart from each other. They don't interact with each other. They are not limited in any way. They have all the freedom to dissipate energy without having to worry about the other particles. So the gas will have, in a way, the maximum amount of freedom to dissipate energy. That's why a gas state will have a higher entropy. So all this discussion comes to summarize that all you have to remember when looking at a chemical reaction is that the entropy of a solid is smaller than the entropy of a liquid, and then that is smaller than the entropy of the gas. So at this point, we are not that much interested in calculating what the changing entropy is, but what is the sign. So when we are looking at states, changes of state, basically what we are aiming is what is the sign of delta S. Okay, so that's the question that we are trying to answer. We are at this point, we don't want to know, or we don't want to calculate the changing entropy. We just want to know, is the entropy positive or is the entropy negative? The changing entropy is negative. And we can do that by just looking at the chemical reaction and taking a look at the particular state in which those substances are present. So in this particular case, okay? So we have three reactions, and then we want to predict whether the entropy is going to be negative, or the changing entropy going to be negative or positive. And pretty much what you are trying to, the way we can look at this is, if the changing entropy is equal to the entropy of the products minus the entropy of the reactants, okay? Then if the entropy, and by the way, the entropy, these quantities here, this and that, they are always positive, okay? Entropies are always positive. So therefore, in this particular case, if you are calculating the changing entropy, and the entropy of the product is larger than the entropy of the reactants, and let's write that down. If the entropy of the products is larger or greater than the entropy of the reactants, then the changing entropy not equal but is positive. Okay, and the other way around, if the entropy of the products is smaller than the entropy of the reactants, then the changing entropy is going to be negative. Okay, so all we have to do here is to determine whether the changing entropy of the reactants is greater or smaller than the entropy of the products, and based on that determine what the sign of the changing entropy will be. So in the first reaction we have water, okay, water in the gas phase going to water in the liquid phase. And based on our discussion, the gas phase, for now, anything in the gas phase will have a larger entropy than anything on the liquid phase. At the qualitative level, we're going to just keep it like that. We are not calculating anything, just determining what the sign is. So anything in the gas phase has a larger entropy than anything on the liquid phase. Therefore, in this particular case, for the first reaction, the entropy of the products is smaller than the entropy of the reactants. Therefore, the first reaction, this one over here, delta S is going to be negative. Okay, so again, the entropy of the products is smaller than entropy of the reactants. Therefore, delta S is going to be equal to 0. Now, the next one is a good problem. Solid carbon dioxide sublimes. And what does that mean? Well, you have solid carbon dioxide, correct? So carbon dioxide in the solid phase sublimes, and that means, well, if you have seen a piece of dry ice, well, the dry ice doesn't become a liquid, right? It just evaporates. So that's the sublimation process. Sublimation is going from solid to gas. Therefore, here CO2 means you are going from the solid phase to the gas phase. Now you're comparing the entropy of a gas with the entropy of a solid. Therefore, the entropy, not the change, in this case, the entropy of the products is larger than the entropy of the reactants. Okay, therefore for this one, delta S is positive. Excuse me. Now the last one, it could be a little trickier because everything is in the gas phase. Okay, now what do you do there? Okay, so let's change color here. So we are looking at this reaction. Okay, and everything in this reaction is in the gas phase. Well, if everything is in the gas phase, then you just count to the number to the number of moles. You just count the number of moles of gas that you have at each side of the reaction. And whichever has the highest number of moles in the gas phase will have a larger delta S. For instance, if I rewrite the equation, we have 2N2O gas that goes to 2N2 gas plus oxygen gas. So in the reactant side you have 2 moles of gas. In the product side you have 2 plus 1, that is 3 moles of gas. 2 moles on the reactant side, 3 moles in the product side. Therefore, because you have all gaseous species here in this reaction, the side with the largest number of moles of gas will have a larger entropy. So in this case, then the entropy of the products is larger than the entropy of the reactants, and therefore for this, delta S is larger than 0. It's positive. Okay? So that's how you approach this problem. So you look at the gas, solid, liquid, and then make a prediction based on what you see at each side of the reaction. Okay? So let's try this one more time. So we have boiling water. And boiling water, well, what is the process? So you have liquid water, and you are taking that liquid water to the gas phase, right? So the process is water in the liquid phase goes to water in the gas phase. Therefore, here, delta S. The entropy of the products is larger than the entropy of the reactants. Okay? And therefore, delta S is positive. In the next reaction, we have iodine going to the gas phase, from the gas phase to the solid phase. So here, the entropy of the products is smaller than the entropy of the reactants, and therefore delta S is negative. Okay? And now here we have an interesting case because we have solids and you have a gas. Okay? And it doesn't matter how many solids or how many gases you have there. For in this case, remember, if there is a gas, then you just focus your attention on the gas. It doesn't matter what substances you have there. The entropy that a gas will have is large enough that for these practical purposes, the entropy of the gas will control the entropy outcome, the changing entropy of the reaction. So therefore, if we are focusing on the gas phase, if there wasn't CO2 here in the gas phase, well, you have to change your analysis, but because you have 1 mole of gas here, but in the reactant side you have 0 moles of gas, then the entropy of the products here is larger than the entropy of the reactants, even if it's just by 1 mole. Okay, so in this case, entropy of the products larger than the entropy of the reactants implies that the changing entropy for this reaction is also positive. Okay, so when it comes to predicting the sign of delta S based on the reaction, well, you focus your attention. You first look for the gas, because the gas will control the entropy, the changing entropy, no matter what. But if there are no gases, then you move on to the next one. So you look at the liquids, at solids. If there are liquids, they're going to have a larger entropy than the solids, and so forth. So, Okay, so at this point, remember, this is just at the qualitative level. You just want to predict what the sign is, and you are doing that based on the state, meaning solid, liquid, or gas, that those substances are in the particular reaction. Okay? Later on, we will do calculations, but for now, it's just about predicting the sign. If I give you a reaction, you should be able to tell me whether the changing entropy for that particular reaction is going to be positive or negative.